We have seen series and parallel combination of the resistors, and we just did how do we connect resistances in series and how do we connect resistances in parallel. Now, we will study what is the total resistance, that is called equivalent resistance in series combination, and what is the equivalent resistance in parallel combination. So, let us see first one is series combination. So, in series combination, first we will draw circuit diagram. Suppose there are the 3 resistors as we join in the previous diagram. This is R2 and this is R3. These 3 resistances are connected in series. Now, we connect a battery here. This is plus minus. Just we connect here a key, and then we can connect a device which is used to measure current. This is negative and positive terminal of this, and see here positive terminal of this device is connected to positive terminal of the battery. Now, when we switch on here, plug the key, we get current flows like this. Direction of current is positive to negative. As you know, this is a conventional direction of current. So, in series combination, see here I remains constant throughout the circuit, It means unless you change V here, you cannot change the current. So, I is same for the R1, R2 and R3, but potential difference across these, if you connect here the voltmeter, you will find all these voltmeters will show different readings. So, first one we can name is at V1, V2 and V3. As we have done Ohm's law, V is directly proportional to I and V is equal to Ri. Similarly, we can apply Ohm's law in this combination also. So, first if you apply Ohm's law for V1 for the first resistor R1, so we can write V1 is equal to R1 I, V2 is equal to R2 I and V3 is equal to R3 I. This is just I am writing according to Ohm's law. So, Ohm's law is applicable for the single resistor as well as for the combination of the resistors. Now, see here this total potential is V, which has now been divided into 3 parts V1, V2 and V3. But if you add all these, you will be getting V is equal to V1 plus V2 plus V3. So, we can write IR1 plus IR2 plus IR3. Now, this V is the total V. So, we can write here Ri. This R is called Rs I have given. Rs is total resistance in series. So, here we can solve it further. We can cancel, I take common and from here I will get cancelled and we will be getting here Rs is equal to R1 plus R2 plus R3. So, this is called equivalent resistance in series. So, if the 3 resistors R1, R2 and R3 are connected in series, equivalent resistance is sum of all the 3 resistances. Now, one more important thing is here, you see the equivalent resistance, that means the total resistance is greater than any one of the resistance, right. So, when we combine all these devices or all these resistors in series, we get equivalent resistance higher than the any individual resistance. So, wherever you need very high resistance, or then you can take this combination, series combination can be applied. So, now look at all these parts here in the series combination, what are the main thing, how does the V1, V2, V3 gets divided, and but I remains constant, this you have to take care of, and every time you have to see I remains constant in the series combination. Okay, we have done series combination and seen total resistance in the circuit. Total resistance is sum of all the individual resistances, which is higher than any individual resistance. Now we will study parallel combination of the resistors. So see here, the parallel combination. See, in parallel combination, if you have taken 3 resistors R1, R2 and R3, you connect them, these 3 here, take a common point and just you connect here a battery, and then you connect here an ammeter, and I have connected here a key. This is a complete circuit. Here this is again positive negative, this is plus minus, this is V, and current will flow from here. Now see, in series combination I was same for all the resistors, but in parallel combination, see, as this I comes at this point, it has 3 different paths. So it goes here as I1, I2 and I3. This I1, I2 and I3 have different values. They cannot be same unless R1, R2 and R3 are same. So see here, I1 current has divided into 3 parts, I1, I2 and I3, but V remains same for all these 3 resistors. So here you will write V remains same, and I gets I divides in 3 parts. Basically they divides in 3 parts I have written here, but it depends on the number of the resistors. So whatever the number of resistor, according to that I gets divided. Now we will apply again Ohm's law. As I have told you this thing, we can apply Ohm's law for the single resistor as well as for the combination of resistors. So now we will apply Ohm's law for the first one. If you apply, so we know it, V is equal to Ri, so we can write I is equal to V upon R. According to this, here we can write I1 is equal to V upon R1, I2 is equal to V upon R2 and I3 is equal to V upon R3. See here, as I told, V remains same. So here also V is same for all these 3 resistors. Now total current I is equal to, we can write I1 plus I2 plus I3. So we can write V upon R1 plus V upon R2 plus V upon R3. Now here this is the total I. So for this we can take total resistance of this complete part. Suppose this total resistance is R, so we can write V upon Rp. Rp is the total resistance of this one. It means this is the combined resistance of R1, R2 and R3. So now we can cancel here, and we will be getting 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So total resistance is actually the sum of the reciprocal of each resistors. That means total resistance is less than the value of any individual resistance. And here in parallel combination we get less resistance as effective one, but in series combination effective resistance was much larger. Here, so where do we prefer series combination? Where do we prefer parallel combination? We will see in the different types of circuits. See here, like for the domestic circuits we prefer parallel combination. Why do we prefer parallel combination? Why do we not prefer series combination, right? So we have to study in detail, right? So we will study later on all these things.